we're going to start looking at work, energy, and power. So it's part of mechanics. And here we go. So, Unit 1, when we look at work, we often think that when we go home and we do homework, that we're doing work, and perhaps we are, but that's the English sense of the word. Work for us in terms of physics is different. When work is done, in order for work to be done in physics, what we need is we need a force to act on the object, and we need the object to move in the direction of that force. So there has to be movement and there has to be a force. When we look at an example of an object on a table, now remember, my object could also have a downward force because of course there's gravity, but that really is irrelevant because the point here is that the object isn't moving. It's not going up or down, which therefore means that no work is being done even though a force has been applied. If we now look at the same object that's being picked up, there is a displacement, there's movement upwards, and there's an upward force. That means there's now work being done in the science sense of the word, where we say where now there's force and displacement in the same direction. However, if I'm still applying an upward force and my object moves sideways as shown here, so my girl is holding the object upwards but is moving to the left with the object, still no work is being done because the displacement is at 90 degrees to the force. Remember, what we said in the first part is that the force and the displacement must be in the same direction. So that gets us to a definition. Now this is starting to get us to the official definition, which says to us, if a constant force acts on a body and it undergoes a displacement, then the work done by this force can be defined as followed. So here we have the situation with a box. Okay, here's my force. Now remember, when we look at this, we're actually concerned with the horizontal force, and we've done earlier that my horizontal force is F cos theta. Remember, when we put it into its components, the horizontal force is F cos theta. So theta is really important because we're looking at the horizontal displacement. So that tells us the work done on an object by a constant force is F delta x cos theta, where F is the magnitude of the force, delta x is the magnitude of the displacement, and theta is the angle between the displacement and the force, which is really, really important. That gets us to our equation, where W equals F delta x cos theta. W is work, which is measured in joules. F is force, measured in newtons. And delta x is displacement, measured in meters. Those are all important. And theta is the angle between F and delta x. Please note, work is a scalar, therefore it has no direction. However, work can absolutely be negative. It's the only scalar we work with that can be negative, because the negative tells me about how the energy is either being put into the system or being taken out of the system. So it's very, very important. Work done is energy transferred. Now this energy could be transferred to the system, which means maybe it speeds up, or it's energy that's taken out of the system, which means that either it slows down or we have a transfer of heat, we get sound, all of those sort of things. Okay, so you need to work through the activity. The memos are on Teams. Okay, if we look at network, there's a couple of ways we can do that. So there's always a lot of forces acting on an object. Those forces, we've learned before, can be net forces. Okay, so we've got to look at the effect of direction of a force and the displacement. When the force is in the same direction as the displacement, so my force is going to the right and my displacement is to the right, F and X are in the same direction, which I've said before, delta theta is 0 and cos theta equals 1. All right, because cos 0 is 1. Positive work is being done. That means we are adding energy to the system. Okay, we're giving it extra energy. When they're in opposite directions, so the force is to the right and delta x is to the left, so this would be something like friction, which always acts in the opposite direction. That means theta is now 180, and cos 180 is minus 1. That means that negative work is being done. That means that we are taking energy out of the system. So kinetic energy, for example, is becoming heat. The total energy of the system is decreasing, all right? And it's going to the surroundings. Then we get perpendicular displacement and forces. Now here, and this is just an MB, remember friction is always at 180. Friction acts, say, to the right, and the displacement is down, please, or the force acts to the right, displacement is down. There's lots of ways we can do this. We're not going to worry too much about whether where this happens. You'll see them as we go along. But here, friction, the force could be left or right, and the displacement could be up or down. It doesn't matter. The point here is that F and delta x are perpendicular, which means theta is 90, and cos 90 is 0. So no work is done by this force, all right? Because this force, this displacement at 90 degrees to each other. Let's look at this example. We want to calculate the work done on a block of ice by a person exerting a 200 Newton force if the block is displaced by 5 meters to the right as shown. What's important here is that they've given you theta. It doesn't matter that the force is being pushed down. That's irrelevant. Whether it's being pulled or pushed, it doesn't matter. The point is the angle. So, F is 200, theta is 5 meters, sorry, cos is delta x is 5 meters and theta is 25. This is a straightforward substitution, and he does 906.31 joules of work. We're not concerned how that work gets translated, but that's how much energy he's doing. If now we change the situation and he now pulls the block of ice, remember again, it doesn't matter whether he's pushing or pulling. What's important is now x, theta, has changed to 30 degrees. That's the important part here. So if F is 200, same as delta x is still 5, theta is 30, we get a smaller amount of work done. The bigger theta becomes, the smaller the amount of work done. Okay? How much energy is transferred in both examples? Well, the energy transferred is the amount of work done. Energy in number 1 is 906.31, and in number 2, 866.03. So please remember, and I'm just going to write it in here for you, all right, that work decreases, okay, when theta increases. Okay, that's really important. Maximum work is done when theta equals 0, okay? Or 180, it's just going to be work that's negative, okay? Minimum work, all right, is when theta equals 90 degrees. And we want to try work with the theta that's either going to be between 0 to 90 or at 180. We don't want to work with anything in between that, okay? So, a 100-gram apple is thrown, so the apple is moving up and reaches a height of 4 meters. Gravity always acts down. There's absolutely no exception to that. They want the work done by the gravitational force on the apple. Well, theta is delta x is 4. Theta is 180 because the apple is going up, but is going up, but gravity acts down. Gravity is going to be F equals mg. It's how we work out gravity. So the force the apple is experiencing is 0.98 newtons. Straightforward substitution. We get a negative value because as the apple is moving up, my apple is losing kinetic energy. It's getting slower and slower and slower. So negative work is happening. Work is being transferred to the surroundings. When we calculate net work done, the net work is the sum of all the work done by the individual forces on the object. There are two ways we can do this. My preference is the second, but it really is up to you. Best way to do this is an example. So a truck of mass 2,000 kilograms, free wheels, which means brakes aren't being applied, the foot isn't on the accelerator, they're allowing it to just move under the force of gravity, down a long, 30-meter long incline. So what they are saying to us is that the distance, delta x, that the truck is going to move is going to be 30 meters. The plane is inclined at 30 degrees. The truck experiences a frictional force, of 5,500. So that's in that direction. Please don't forget, and this is one that's going to happen often, there's still gravity. Okay? Gravity is still acting on the object. And in fact, it's going to be FG parallel. That's the important one here. Because only part of gravity is acting on the object, because that's the part that pulls it down the slope. So what I actually kept forgetting to put in here is the question is this. Okay, calculate the net work done on the truck. That's the calculation, okay? We're going to do it two ways. So the first thing, please, a free body diagram is incredibly useful, because a free body diagram allows us to know how the forces are acting. So there's the free body diagram. Of course, I have left out a force, which is over here, which is Fn, but I left it out because it acts at 90 degrees to the motion. It's not going to do any work. Okay, so first method, we're going to calculate the work done by each of the forces. So the first one is work done by friction. Friction is always cos 180, and it's minus 165,000 joules. Okay, that one's easy. Now we need to do the work done by gravity. When we look at gravity, now we've got to go, why am I using cos 60? First of all, that there is for the calculation of gravity. That's mg, okay? The 60 comes from this. So my force is acting down. My object is acting in that direction. That angle there, because that is 90, that gives me 60. It's one of the reasons why I personally do not like this method, because you often get that 60 degrees wrong. Okay? That gives us 294,000 joules of energy. Now we can go, well, W net is WG plus WF, work done by gravity, work done by friction. We never change the negative work to a positive. It stays as a negative. So the total work done on my object is 129,000 joules of energy. That will translate into a change in kinetic energy for my truck. That's the first way. The second method is this. F net equals Fg parallel plus Ff. I'm working out the net force parallel on the slope. Fg parallel, remember, is Fg sine theta minus force of friction. That's from grade 11. 2,000, that's the mass of the truck, times 9,8 sine 30, okay, minus 5,550, 4,300 newtons, okay? That's the net force. It's a positive net force, which means net force is in the direction of the motion. Theta is then going to be 0. 4,300 times 30, that's 30 is the distance. Oh, look, 129,000 joules. Same thing. You will eventually find a method that makes sense for you, but sometimes they will specify. Which means now you need to go through activity 1 on page 161.